Hello, everyone. My name is Nick Manning. I am a PhD student from Michigan State University's Center for Systems Integration and Sustainability. And today I'm going to be talking about uncertainty and introducing meta-uncertainty. So everyone here has probably seen this quote from George E.P. Box: "All models are wrong, but some are useful." Today, I want us to think a little bit outside of the EP box and say all models are wrong and uncertain, but some are nonetheless still useful. I want to think about the modeling process as a whole. Some of the first steps when you're designing some of these models, have some phenomena you're interested in, and then usually we'll place this into the context of some framework. So for example, we're in Illinois, the largest soybean producing state in the US, and soybean trade is actually really, really important, as well, as soybean was the most imported and exported crop in 2023. So if we can take that phenomena and put it into some conceptual framework like coupled human natural systems, we've talked a lot about a lot of different types of frameworks today already. So to spend one quick second on coupled human natural systems, it's essentially looking at not just the human system, so the farmer and the trade and laws they have to follow, or the natural system, so the soybeans and the abiotic and biotic components of the environment. It's thinking of both of these in tandem as one coupled human and natural system. The next step then is often to design some sort of research method and ask a question. So we might want to know the impact of price on agricultural expansion and use some sort of interrupted time series design. Next, we have our research methods. So we might try and quantify this by finding different data sources, plotting it, looking at this change across time, and then lastly, evaluate how well our model did. What are our results and how do they compare to the real world? However, uncertainty compounds across each of these steps. You have different sources of uncertainty coming in different phases and from different sources. And also the evaluation methods to look at these uncertainties might just report standard values and not discuss actually where these sources are coming from. So to address that, we're introducing the term meta-uncertainty, which is essentially just uncertainty about our uncertainties. This is not only focusing on about how uncertain we are, it's also thinking on how we are uncertain. So what are the reasons why we are seeing the uncertainty values that we are seeing? Today, our study today focuses on two main objectives. One is developing a typology for classifying meta-uncertainty in coupled human natural systems or CHANS models, and then also to design how model uncertainty has been quantified and communicated across the literature. So beginning with that first objective, a more formal definition of this can be the assessment of the aggregated or interactive effects of different uncertainty sources within some modeling framework. We're not just looking at the empirical observations and how they compare to the real world, but we're also trying to ascribe the different sources of uncertainty to these values. And we're not just interested in the contribution of each source of uncertainty, we're also interested in the way that these sources interact with one another. So you might have saw this quick figure on the other frame, on one of the other slides, but this is the 6 main principles that we're covering today. And each of these is a principle of meta-uncertainty that modeling techniques will often try and evaluate on their own. To go through them one by one really quickly, first is knowledge of the system. So this is that the models that we're using might not fully represent the systems that we're studying, and oftentimes they can't fully represent the systems that we're studying, as these are very, very complex systems with different forms of phenomena happening at the same time. Next is model specification, which I think that some of the previous talks have mentioned as well. So unknown parameters, boundary conditions, or the choice of modeling approach. Anytime you're trying to abstract some phenomena into a model, you have to choose a method to do that, and that comes with some inherent limitations. Next is spatial and temporal scale issues. So these are issues derived from coarse model predictions or model input data. Also computing limitations. So we've heard, I think the first day I was here, there was a talk on quantum and AI. And so these computing power is increasing and increasing. But with that, we're also seeing an increase in the complexity of the questions that we're asking. So these two together are making this imbalance between, we are still seeing computing limitations despite this increase in computing power. Fifth is spatial dependence and heterogeneity. So this deals with spatial autocorrelation and neighborhood effects. Often quantitative analytical techniques will think about the data as independent, and a lot of the spatial dependence problems kind of violate that assumption. And then lastly, empirical data limitations. Sometimes there's just not great data available, or the data quality and availability is hard to determine. Also model extrapolation. So we're looking, if we want to look forward in time, maybe the data is not there along that extrapolation. So an ideal coupled human natural meta uncertainty approach would think about all of these together, or at least touch on and discuss most of them. Next, we're going to assess how model uncertainty has been quantified and communicated across the literature. To do this, we performed a literature review across Web of Science and Scopus. Initially, we found about 300 studies, and after some brief screening for time, language, and if they actually included some kind of Chan's model, we were left with 175 studies. We had several different people reviewing these different papers. So we had, I think, 12 independent reviewers, and not including myself and my co-author, Andrés. And so each person would answer these questions about each study. So they would ask, does it include a model? How do they quantify their uncertainty? And does that model uncertainty approach fall into any of the categories that we mentioned? So getting into some of those results, from that 175, only 109 of those quantified their uncertainty in some way. We saw that typically people are focusing on their model choices and model specification, and often computing limitations were not addressed. Here we can look at the interactions between those. That's something that I mentioned with meta uncertainty. So the way that you read this is that this is the 1-to-1 line. And so although these both are 36, this is 36% of 81. So it's going to be a little bit lighter color than that darker one. We saw that model specification and knowledge of the system were evaluated together most often numerically. And then by percentage, spatial dependence and heterogeneity and empirical data limitations, both evaluated with model specification, was the second sort of most common approaches. We also saw a general trend towards quantification in the literature over time. So this might not have been as common in the early 2000s. We also just didn't have as many papers that did quantify their studies. But as we move forward in time, more and more studies were quantifying their approaches to uncertainty. So this proves a good trend in the literature about thinking of uncertainty in Chan's modeling. We can also plot this spatially. So we saw that most of our studies came from the US, Iran, and China, with other being another main category. That's essentially just regions with transboundary areas that might not map well to one country. However, we can see with 6 different categories and 2 other different categories, including none and other, this is pretty hard to read and derive any useful knowledge from. So we can group this one level up into these 3 major categories. System. So if we're thinking about problems in the system, knowledge of the system and model specification, data, and unit of analysis. We can look back at this and see that most of these studies are focused on problems and uncertainty with the systems across the world. Next, we can take this data and actually put it to use somehow, so we can operationalize this through uses of ternary diagrams. I wanted to mention this as this is going to be really important for researchers on their own to sort of plot their data on and see where they could do more different uncertainty quantification. And also this is useful for decision makers to see where their certain model will plot on this ternary diagram, and they can know the common areas that this model might not be as good at addressing. However, these kind of diagrams are often not as common. They're usually only common in like plant and soil sciences. So for a second, I'm going to take a quick second and look at how to actually read one of these. So if we have that point right there, I usually will start from the bottom and go up. So 0, 20, 40, 60 for the red, and then go over for the blue. So then if you go up from the bottom, you can see that that's 60. Go over from the blue from the right, 0, 20, 40, 60, 80, 100. So then that would be 20 for blue. And then last, going over from the left, 0, 20, 40, 60, 80, 100. And so going over from there, that would be 20. So 60, 20, 20. A quick example that will show why dark chocolate is the superior dessert. Going up from 0, we can see that this is a certain amount, 73% chocolate. Going over from the right, the amount of milk in dark chocolate is 0 on the red. And then going over from the blue, you can see that it's about 27 or the rest of that percentage. So just to reorient ourselves with maybe a more accessible example there. In our literature review, we asked the question, does this model, so for each study, does the model uncertainty approach fall into any of the following categories? And this is that group response. So our blue lines, or I'll start with our red, going up is the unit of analysis, going over from the right is the system, and then going over from the left is the data. From this, we can see that uncertainty approaches evaluating the system, so model specification or knowledge of the system, are most commonly evaluated by themselves and are the most frequently evaluated category. So that bottom right corner, if you go over, that's 0, 0, and then 42%. We also can see from this that unit of analysis remains a common source of uncertainty in Chan's models, so this was not typically evaluated. This line going up is the 50% line. So anything below this line would have been at least one of the sources evaluated. And on that bottom line, that bottom line is 0 of the unit of analysis. So this means the unit was not evaluated in any of those studies. And that was over 2/3 of our studies did not look at the unit of analysis. And then lastly, in the middle, only 9% of studies focused evenly on some aspect of uncertainty. So some future work here, it would be really great to determine how this uncertainty, so now that we've plotted it, we know in the literature this trend, how does that actually influence model usefulness across this decision making? And that's something that we're going to be kind of probing different studies and different disciplines to evaluate. So if you have any insights on this, please find me at the coffee break. I know that I'm holding you all from. And then another future work is to quantify the amount of uncertainty from each source. So right now, the way that we plotted it is, does this evaluate it? But it's not saying how much of the uncertainty is evaluated in those methods. So for example, something on that bottom line might use one of the model techniques and one of the system techniques. So that's 50-50, but almost all of the uncertainty could be coming from one of those different sources. And we're not really evaluating that yet. So that's something else we would like to look into. Takeaways are that acknowledging meta uncertainty can help identify the sources of our uncertainty and go beyond those single values in our evaluation techniques. Over roughly 2/3 of our study quantified uncertainty, but only 25% addressed more than one uncertainty principle, with a more trend moving towards quantifying your uncertainty. And lastly, uncertainty sources in the system were assessed most frequently, and unit of analysis sources, so spatial temporal, scale, and spatial dependence, were not commonly assessed. And I want to remind everyone that thinking outside of the box can help us when we are identifying our model uncertainty. I want to take a second and thank all the over a dozen reviewers that worked alongside us. Most of the team was from iGuide, but some people from the Center for Systems Integration and Sustainability as well. And thank you all for listening. I'm happy to take any questions within your remaining time.